Last class we discussed the equations of equilibrium in cylindrical polar coordinates, and there we have seen that there are three equations, and the three equations are in r, theta, and z coordinates, and they have to be solved for solving solid mechanics or elasticity problems. But the problem is that to solve them analytically is not simple, and often we have to make assumptions or we have to simplify the equations. And it is for simplification, there are certain cases. We cannot simplify all the cases. There are certain cases like solids of revolution where we can simplify matters. Now, I told you earlier, I'll tell you again, solids of revolution are nothing but if you revolve a curved surface about an axis, then you get a solids of revolution. And the simple examples are cylinders, rotating disk, and many other shapes like this, which are symmetrical about the axis of revolution. And because of the symmetry, it becomes independent of angular coordinate. So we can simply write that del by del theta is 0. This is one of the conditions. Now, there are many axisymmetric problems, but we'll consider only few. So first we'll look at the cylinders, and then we'll look at the rotating disk. Now cylinders again are many types, but looking on the basis of their wall thickness, there are mainly two: thin cylinders and thick cylinders. Thin cylinders we'll consider first, and I think you have already done this in your earlier courses, but for the sake of completeness, I will go through it again. Now, a thin cylinder is the one where the wall thickness is less than 10% of the radius. And for all cylinders, thick and thin, there are mainly three types of stresses: internal or external pressure. The circumferential or hoop stress. This is figure A is the example. Hoop stress or circumferential, the stress is along the circumference. So if it splits or if it bursts, it will burst along the circumference. That's why it is called circumferential or the hoop stress. And we have already seen in our earlier courses that it is given by PR by T, P being the internal pressure, R being the radius of the cylinder, and T being the wall thickness. And the second type of stress that will be generated here is the longitudinal stress. That means the stress along the length of the cylinder. Now, obviously, this stress cannot be there unless the ends are sealed. For many cases, for example, hydraulic pipes carrying high pressure liquid, ends are not sealed. So there, that stress does not apply. But we consider this, considering that the ends are sealed, then it will, if it splits, it will split along the length. And the longitudinal stress is given by PR by 2T. Again, P is the internal pressure, R is the radius, and T is the thickness. And then there will be radial stress, which is directed along the radius on the surface, internal surface of the cylinder. We'll discuss more about this later on. But for thin cylinders, this radial stress and the variation of sigma theta and sigma T, or sigma L or sigma Z. That means the circumferential stress and the longitudinal stresses. Variation of these stresses across the thickness are negligible because the thickness itself is small. So its variation we do not consider. So here it's very simple. we have got only two stresses, circumferential of the hoop stress and then longitudinal stress. I do not know if somebody has already told you before, you must remember that both these stresses are principal stresses. That is because no shear stress can exist here, otherwise it will deform. And for a uniform stress across inside the cylinder, shear stresses cannot exist. And hence, both sigma theta and sigma L or sigma Z are principal stresses. Remember this. Now we'll have a quick look at the derivation of these stresses. I know you have already done it, but let's do it for the completeness. So we take a small section and cut out section from the cylinder, and we see that there is an internal pressure P and the radius R. Now here, the pressure inside the cylinder produces stresses at the cutout section. So there will be a sigma theta at the circumferential stress along the cutout section. And we have got internal pressure over the whole area. Now let's see how to do the force balance. What is the force developed due to the pressure? Consider a small element of delta theta at a distance of theta from the vertical. So what is the area on this? The area of this small element is RD theta into L. RD theta is this arc and L is the length. So RD theta into L multiplied by P is the force along this direction. But we need the force in the vertical direction because we have developed the stresses sigma theta along the vertical direction on the circumference. So let's take the cos component of this force, and we have got PR d theta L cos theta, and that will be equal to 2 sigma theta LT, because sigma theta is acting on thickness T and the length L. So the area is T into L and multiplied by sigma theta. And there are two such things because there are two sides. So it is 2 sigma theta L into T. So on the left hand side, you have got an integrated force over the whole area, internal area, and that will be integrated 0 to pi by 2 into 2 PR d theta L cos theta. And on the right hand side, you have got 2 sigma theta LT. And if you do the simple integration, you will find out you get PRL, 2 PRL. Okay, 2 PRL, and on the right hand side, 2 sigma theta LT. So sigma theta is simply PR by T, because L and L cancels out, and you are left with PR by T. That's the simplest derivation of the circumferential or hoop stress that we always use. Now let's look at the longitudinal stress. For this, we take a longitudinal cutout section, and the pressure inside is acting along the radius, and the force developed due to this pressure will be P multiplied by the projected area. What is the projected area? Projected area will be pi r square, I square actually, but I've simply written it as r square. P into r square is the force due to the pressure acting on this curved surface. And what is the stress developed due to this pressure? That is sigma Z or sigma L or whatever you write. So here I've written sigma z, and the area, this is an annulus area. So the area is pi r o squared outside radius minus pi r I squared. And this is the total area on which sigma z is acting. So the force will be sigma z pi r o square minus r I square. Now what is r o square minus r I square? Here we make assumptions that r o is almost equal to r I, and let's say it's equal to r. But we cannot ignore that there is a thickness. So we have to say r o minus r I is equal to t. So this whole thing, pi r o square minus r I square is equal to pi into 2 r o minus r I into r o plus r I. R o plus r I is 2r because both are equal to r, and r o minus r I is equal to t. So it becomes pi 2 RT. So it's very simple. So sigma z, and this is the right hand side, and this is the left hand side. So sigma z equal to PR, on r cancels out, pi cancels out. So you're left with PR by 2t. Okay. So remember that longitudinal stress is half of the circumferential stress, because circumferential stress sigma theta is PR by t, and longitudinal stress is PR by 2t. So this is simple, and we all know it before in the earlier semester. Now let's go to the thick cylinders. Now in thick cylinders, the approach will be a little different, because here the stress variation across the thickness of the wall has to be considered. And the typical examples are gun barrels, hydraulic pipes carrying high pressure fluids, and so and so. So we have to consider this as axisymmetric about the z-axis. As I was saying, that these cylinders, thin and thick, both are axisymmetric about z-axis. And the equations of equilibrium, we have to consider in cylindrical polar coordinates, 3 equations of equilibrium. Now this becomes difficult, as I was saying. So let's see that what assumptions we can make. For axisymmetric problems, there is one advantage, that the deformation is uniform about an axis, and hence we can say that del by del theta is 0, as I have said earlier. And also, in most of the cases of thick cylinders, the ends are not sealed, and ends can extend freely. So we can take sigma z equal to 0. And it is because of the symmetry, radial deformation, and symmetry, tau r z, tau theta z, tau r theta, they are all 0. Okay, all the shear stresses are 0. So if we apply this in our equations of equilibrium, let's see what we get. Let's take the first equation. In the first equation, del sigma r by del r is there. That is no change. Second term is del tau r theta by del theta. Firstly, del by del theta is 0, and secondly, tau r theta is also 0. The second term vanishes. Third term also consists of tau rz, and tau rz is also 0. So third term vanishes. So we are left with first and the last term. So we can write del sigma r by del r plus sigma r minus sigma theta by r equal to 0. Okay. So the first and the last term remains. Let's look at the second equation. In the second equation, first term has got tau r theta, which is 0, according to our assumption. And here it is del by, second term is del by del theta, variation with respect to theta. That is also 0. Third term has got tau theta z, that is also 0. And the last term is tau theta r, that is also 0. So the whole of the second equation vanishes. We don't have to consider that. Third equation, tau zr, first term, that is 0. Tau theta z, second term, that is 0. Third term, sigma z is also 0. And tau zr is also 0. So the third equation also vanishes. So we are left with only one equation, and that is only a part of it. The first equation, second and third term is not existing. So we are left with the first and the fourth term. So we have got, this is the only reduced form of the equation, and see how simple it is. From the three general form of equation, we have reduced it to a simple equation to solve. So for thick cylinder, if we solve this equation, we can get all the stresses. Now, this is, let's look back here. These equations are true only for static equilibrium and without body forces. But let's generalize it a little bit. If we consider the rotating disk and the thick cylinder may rotate or may not rotate, but rotating disk always rotate. So we can add a body force term, which will be the centrifugal force rho omega square r, to make it more general. So this equation, you can write it in a general form: del sigma r by del r plus sigma r minus sigma theta by r plus rho omega square r equal to 0, where omega is the angular speed, rho is the density, and r is the radius. Now this equation we can write it in a little different way, just by taking this r, multiplying the whole thing by r, and we get sigma r plus r del sigma r by del r minus sigma theta plus rho omega square r square equal to 0. You see here, this equation is simple, but there are two variables, sigma r and sigma theta. From now on, we'll try to reduce this equation to a single variable, and all our efforts will be to do that. In order to do that, we have to consider strain. Now the strains that we have seen in the Cartesian coordinate, epsilon x, epsilon y, epsilon z, del u by del x, del v by del y, del w by del z, in polar or cylindrical polar coordinate, things are a little different. But we'll look at it from a very basic concept. Take the radial line and take a small length AB, and let it be displaced to A dash B dash. So A has moved from A to A dash, and that will be the displacement in the radial direction UR. Now the point B has moved from B to B dash, so there will be an increment due to the length. And this increment is, as we always know, we take the gradient and multiply it with the length. So UR plus del UR by del R into delta R. UR plus del UR by del R into delta R is BB dash. So what is the strain? Strain is the total change divided by the original length. total change is UR plus del UR by del R delta R minus UR. So this minus, that was the initial change, minus UR divided by delta R is the length of this AB. So this gives us del UR by del R. Okay. So that is fairly similar to what we get for Cartesian coordinate, del U by del X. But here it is del UR by del R. And this, if we use a constitutive rule, then this will be equal to 1 by E sigma R minus nu sigma theta, because we are not considering sigma Z. We have said sigma Z is 0. So epsilon R is equal to del UR by del R equal to 1 by E sigma R minus nu sigma theta. Now epsilon theta we have to consider very carefully. What is epsilon theta? Epsilon theta is the change in arc. So let's take an arc A dash and B dash. The distance of A dash and the angle, the change in angle is delta theta. Distance of A dash from the origin is R, and its elongation in the R direction is UR. We are still taking a line along the radius and looking at it from the angular change point of view. So what is the angular change at BB dash? That will be R plus UR, that is the length, total length, multiplied by delta theta. R plus UR multiplied by delta theta is the arc BB dash. Okay. R plus UR multiplied by delta theta is the arc BB dash. Okay. And what was the initial arc? Initial arc was R delta theta. So R delta theta divided by the initial value, which is R delta theta. So if we look at it carefully, we'll see that all this will cancel out and you will be left with UR by R. So the angular strain or epsilon theta is simply UR by R, and that will again be written in Hooke's law as 1 by E sigma theta minus nu sigma R. Let's call this equation 2 and 3. Now let's do some jugglery and see how we can come up with a single useful equation. From 3, you can write UR, take R on the right hand side. You can write UR 1 by E R sigma theta minus nu R sigma R. Simple. Now differentiate this with respect to R, del UR by del R. So you've got 1 by E on the outside, and if you differentiate R sigma theta, R will go, you will be left with sigma theta, and then you differentiate sigma theta, so R will remain, and you've got del sigma theta by del R. Next, you have got nu R sigma R. So you've got nu, when you differentiate with respect to R, R will go out, nu sigma R, and then minus, you differentiate sigma R, so you'll have R del sigma R by del R. So this is the differentiation of UR with respect to R. Now note this carefully and see from equation 2. Equation 2 gives you del UR by del R. So this term will be equal to 1 by E sigma R minus mu sigma theta. So we can, from 2 and 3, we can write 1 by E sigma theta, that is the del U R by del R, whatever we have come up with. 1 by E sigma theta plus A R del sigma theta by del R minus mu sigma R minus mu R del sigma R by del R is equal to 1 by E sigma R minus mu sigma theta. This is simple. This simply we have taken equation 3, derived it with respect to R, and whatever we got, we equated with the delta del U by del R that we get in equation 2. So we get equation 4 in a very simple manner. If you simplify this, you'll get this. All we are writing is R del sigma theta by del R, then mu R del sigma R by del R, then you write sigma theta and sigma R by taking 1 plus mu out, and you will get sigma theta minus sigma R. That is a simple simplification. You can sit down and do it and you get this. So this is the simplified form of this, and we get a nice equation, and let's call this equation 4. So now you see the problem with this equation is this equation is quite good, but problem with this equation, we still have two variables, sigma theta and sigma R. We need to get rid of sigma theta. So how do we do that? Let's look at equation 1. Equation 1 is sigma theta. Let's go back to equation 1. That was equation 1, which we got from the equation of equilibrium, and we can rewrite it here. And all we do is, since we have got del sigma theta by del R, we differentiate this with respect to, you see, in equation 4, we have got del sigma theta by del R and sigma theta. We got to get rid of these two. So equation 1 gives you sigma theta in terms of sigma R. So we differentiate this, del sigma theta del R, and we get R del square sigma R del R square plus R goes out, and we get del sigma by del R, and one more del sigma by del R we get when we differentiate this, and you get 2 del sigma by del R. And when we differentiate this with respect to R, you get 2 rho omega square R. So let's call this equation 5. And this was the previous equation 4. So let's combine 4 and 5. This will take a little time, but you have to be a little careful. Let's substitute the theta terms in equation 4. So we replace del sigma theta by del R from 5. So we got R on the outside, and we multiply R with this, and we get R square del square sigma R by del R square, because we are just simply multiplying R with the del sigma theta by del R, because this is R del sigma theta del R. So R square del sigma R by del R plus 2 R del sigma del R plus 2 rho omega square. 1 R is already there, so you get R square minus whatever was there, we write it, mu R del sigma R by del R. There is no problem. This is in terms of sigma R. And we have got 1 plus mu sigma theta minus sigma r. So there's one more sigma theta we have to get rid of. So all we do is we substitute this sigma theta here. So we rewrite this equation again. R squared del square sigma r by del r square plus 2r sigma del sigma r del r plus 2 rho omega square r square minus whatever was there, nu r del sigma r del r plus 1 plus nu within bracket. We simply substitute this for theta. So we write this. So we get r del sigma r by del r plus sigma r plus rho omega square r square. That is in place of sigma theta. Okay, minus sigma r. Now, bracket closed, and that is equal to 0. Now, let's do a little simplification. Within the bracket, there are two sigma r. One is positive, one is negative. So we cancel it out. This sigma r and this sigma r goes out. And if you multiply r del sigma square by del sigma r by del r with nu, you get this term. So this term and this term cancels out. So you are left with r square del square sigma r by del r square plus there is 2r del sigma r by del r, but there will be one more because there is 1 here. So 1 r del sigma r by del r. So you add this with this and you get 3 del sigma r by del r. Then you have got 2 rho omega square r square. And here you have got 1 rho omega square r square. And if you add them up, you get 3. And there will be a nu, this nu is there. So 1 plus nu, instead of 1 plus nu, you have got 2 here. So there will be 3 plus nu rho omega square r. So if you look at it a little carefully, you'll find out that this is a simple equation that you can get by manipulating these 3 equations. And this is the equation which is the most useful equation, and we'll use this from the next class onward. So that's it for today.